Hello. So this is the last lesson in the energy unit, electromagnetic waves. So that means next time I post something, which will be Monday, it's going to be the assessment over the entire energy unit. Then Tuesday we start the last unit, electricity and magnetism. Okay, so I want you to draw this picture. Just kidding. Don't draw that picture unless you really want to. You can if you want to, but that's not what no. I do want you to look at it though. Let's see. So you have this arrow here, magnetic field, which is represented by these bits of, what do you call it, transverse wave. Y'all know about magnetic fields. You've played with magnets before, I'm sure. Electric field, so one's going up and down. And those two are at right angles to each other, everywhere you look. And both of them are at right angles to the direction this wave is traveling. That's the structure of an electromagnetic wave. Just remember that. And if you want to draw it, go for it, but whatever. So this is the definition of electromagnetic waves. If you notice, there's no notes attached to today's assignment. You're going to have to make your own. Hope you got a sheet of paper out. Electromagnetic waves are alternating electric and magnetic fields. Alrighty. Got that written down? Good. So all waves are made by something that vibrates. These waves are made by vibrating electrons. Now I want you all to think about that for a second. You have electrons in you. Everybody has electrons. Every atom has electrons. Your atoms are all vibrating. Remember thermal energy, temperature? All your atoms are vibrating in place. So all your vibrating atoms are putting off electromagnetic waves. You are giving off electromagnetic waves. Nice little video showing what they look like. So here's a mechanical wave, specifically a transverse wave. So you can see the similarity in structure between mechanical waves and light waves. Light is a version or form of electromagnetic wave. So you see it's two transverse waves at right angles to each other. One's a magnetic field, one's an electric field. And this wave is traveling to the right. There you go. Just need to know that. I don't think you can draw that. If you can, mad props. I can't draw that. Alright, we will learn why vibrating electrons make EM waves. We'll learn about magnetic electricity. For now, just trust me, it happens. Or don't trust me, go look it up. It's your time. It's your life. Have fun. Alright, how fast do these waves go? You know the speed of these waves is 300,000 kilometers per second in a vacuum. That is a rounded off number, but it's close enough for this. Alright, okay, 300,000 kilometers per second. The Earth is only 24,000 kilometers, give or take, around at the equator. Let's round that up to 25,000 for a second. 300,000 divided by 25,000 is the same thing as 300 divided by 25, which is 4, 8, 12. In 1 second, light can go around the Earth 12 times. That's how fast light travels. It's pretty fast. It's faster than your car can go. Light does slow down in denser materials. In air, it slows down a minuscule amount. Something that light can pass through that's really dense will slow it down a lot more. Water slows it down. Glass slows it down. And these things slow it down. Diamonds. Okay, so I want you to look at the shape of this diamond. There's this little part here, all these angles right here, and the point down there, which is being covered up by the pincers that are holding it, but still. Any diamond that is in a piece of jewelry is cut a certain way. And the reason for that is to make sure all the light going in it comes back out the top. Now this isn't diamond, this is plexiglass, so the angles are a little different, but still this shape does the same thing if you get the angles right. If you make it too narrow, the light, some light comes out the top, a lot of it goes back out the bottom. Make it too fat, it all goes out the bottom. So why do you want all the light coming in to bounce around inside the diamond and come back out the top? To make it sparkle. That makes it pretty. I mean, would you buy an ugly diamond? I wouldn't. It's gotta be a pretty one. Alright, an important point. Wave speed only changes when the medium changes. The only thing that controls the speed of a wave is the medium through which it is going. Now, in a previous lesson, you learned about the velocity of a wave and the equation. Velocity of a wave equals frequency times wavelength. If you change the frequency, the velocity won't change. The wavelength will change so that they both multiply together to make the same number. The only thing that changes how fast the wave goes is what it's going through. Y'all gotta drill that into your heads. Changing wavelength does not change speed, it changes the frequency so that they still multiply together to give the same speed, thing I just said. Okay? Alrighty then. Another important point. Electromagnetic waves act like a particle and a wave. So they follow all the rules of waves. Diffraction, refraction, reflection, they behave like waves. But they also affect matter. Remember, waves go through matter. Transverse waves, compressional waves go through matter. But electromagnetic waves also affect matter, which means they have to have some sort of a particle, some sort of mass, some sort of, well, you'll figure it out in a minute. This particle part of the wave is called a photon. So photon, define photon, the particle part of a wave. Okay, moving on. These electromagnetic waves can affect your atoms too. All right, now I'm going to explain to you how EM waves affect atoms. All right, so if you remember, there's both an electric field and a magnetic field in the wave. All right, they're at right angles to each other. Both those types of fields affect charged particles. Okay. Remember, positives attract negatives. Negatives attract positives. Positives repel positives. Negatives repel negatives. You've learned this before me. Refresh that memory. Opposites attract, likes repel. All right, so your electric field is going to affect charged particles. Magnetic fields also affect charged particles. More about that coming on in the next unit, electricity and magnetism. All right. Well, okay, what are you made of? Atoms combine together to make molecules, and atoms have protons and electrons, which are charged particles. So you have charged particles in you. These electromagnetic waves hit your charged particles and make them vibrate more than they already do. In other words, they can warm you up. You want an example? Go out on a sunny day. Just stand there all spread eagle, let the sun hit you. You're going to get warmer because the sunlight, electromagnetic waves from the sun, are vibrating your molecules. So remember, EM waves are made by vibrating electrons. The sun's vibrating electrons are sending that energy down to you in vibrating your atoms. Cool, huh? All right. Higher frequencies will cause atoms to vibrate more rapidly. Same thing as heating up. Now you know how the sun heats you up. Okay? Lower frequencies won't really affect you too much, like radio waves. Let me show you what I mean. So the highest frequencies, shortest wavelengths of EM radiation, will rip atoms apart from each other, destroying molecules. That's a burn. You get sunburn. Or some of us do. I know I do. Alright, let's look at this real quick. I've watched this really poor animation. See how the waves are getting shorter and shorter and shorter and shorter and shorter? That means the frequencies are getting higher and higher and higher. Radio waves down here have the largest wavelengths, which means they have the lowest frequencies. Waves don't come by very often because they're so far apart. Gamma rays have the tiniest little wavelengths, which means they have the greatest frequencies. They'll vibrate your atoms harder and can cause burns. And there's a whole bunch of, well, okay, this is just a natural progression of frequencies down here, but we've subdivided it into something we find useful. And we've named them based on how we use them. One of them is named based on the fact the guy had no idea what he had found, so he said X-rays. Alright, so we're going to go over each of these artificial categories and how we humans use them, and that'll be the bulk of your notes. Here we go. Radio waves. So, these are the largest wavelength, lowest frequencies of EM waves. We use them for communication, such as radios and over-the-air TV. Some of you have digital television. You have the digital antenna somewhere in your house, on top of the house, outside a window, sitting on top of the TV, whatevs. Back when I was a kid, I got a little 10-inch, diagonal 10-inch color TV in my room. When I was a teenager, I was just king of the world. And it was not a flat screen. We didn't have flat screens back then. Guess I'm that old. And it had two huge antennas on it. And a little rabbit ears thing, too. Ask your parents about the rabbit ears, alright? For TV antennas. I'd get UHF and VHF. Alright. The highest frequencies in this range of radio waves, the highest end of those we call microwaves. They're still not going to hurt you. Alright. We also use those for communication. These things use microwaves to communicate with the towers. And we use them for cooking. There's only one frequency they can use for cooking. Your microwave oven has a device in it called a magnetron. Maybe you've seen one, maybe you haven't, I don't know. But when you put electricity to it and turn it on, it creates electromagnetic waves at that frequency. That one little frequency, for some reason, really excites water molecules. So when you're cooking something in the microwave, it has to have water in it or it won't cook. Don't put metal in the microwave because those electromagnetic waves at that frequency also knocks electrons off of the metal, like aluminum foil or whatever. Those electrons shooting off actually put up another electromagnetic wave that goes out and can actually interfere with the magnetron and damage it. So not only are you damaging your microwave internals with scorch marks, you're also damaging the magnetron so it doesn't work anymore and the thing won't cook. Don't do it. Alright, what's that thing? It's a cell tower. This is kind of dated picture. Modern ones, I think, have something slightly differently shaped on it, but whatever. You can recognize it as a cell tower, right? These are microwave transceivers. They transmit and they receive. Alright. These are kind of ugly, so in some places they actually try to make them sort of kind of blend in. So there you go. Fake palm tree with microwave transceivers in it. Conifer. I've actually seen these over by Raleigh, right here. But unfortunately, they're building a new highway there, so they cut down all the artificial pine trees around it. Makes it kind of stand out. If it was in a stand of pine trees, it wouldn't stand out as much. It would serve its purpose. But when you cut down all the trees around it, it doesn't work. It just looks kind of, well, like that by itself. Alright, we also use radio waves for this thing called radar. Radio detecting and ranging. Okay, so it uses radio waves, bounces them off something, and the reflected waves come back and are measured by the radar device to figure out how fast something is moving, what direction it's moving in, where it is, etc., etc. Remember Doppler radar? Yeah, same thing. There's a radar gun. I know if y'all live anywhere near Mount Olive right now, they've got a little radar thingy set up on Brazil Avenue, like going down towards the Pizza Inn. It tells you your speed. It's a 35 zone. Yep, 35 zone. Alright, the next category of electromagnetic waves that we've artificially divided is called the infrared. Infra means below, red is the color red. So these are electromagnetic waves with wavelengths right below what we can see, red. Given off by warm things due to the kinetic energy of the particles. You're giving off infrared right now. You can't see infrared. We have cameras that can see infrared, and they change it into a color picture on a screen so you can see where infrared rays are coming from. I'll show you a picture in a minute. There are actually animals that can see infrared. Hotter you are, the more of these you give off. A group of snakes called the pit vipers. They have eyes, and then above they don't have lips, but above their mouth and below their nose, there's two little pits that are actually infrared detecting organs. so they can see visible light and they can detect or see infrared, which is useful for hunting at night because your prey, they eat mice, is warm. Okay, we also use it, us humans, in remote controls and to read CDs, DVDs, your game playing devices, what, Xbox, PlayStation. I'm not starting that debate. Whichever one you like, you like. I grew up on Atari. Yes, I had an Atari 2600. Heck, when I was 5, we got Pong. Look it up. Pong, P-O-N-G. Alright. So I'm going to show you a picture taken with an infrared camera. The infrared camera detected different amounts of infrared radiation, different frequencies within the infrared range, and changed them into colors we can see. So the higher frequencies, reds to whites, lower frequencies, blues, greens, and even some blacks down there. So this house is losing the most heat right here around this pipe. Oh, this is probably a plumbing thing to get the air in behind the water. And it's losing heat by the windows too, but that's just where houses lose heat. This green thing here is a street sign. And I'm not sure, I've never figured out what that is. Here's a lamppost out in the yard. Okay. You also take infrared pictures of animals. Here's a hellhound. Just kidding, it's not a hellhound. It's a Pomeranian, I think. But you can see where dogs lose most of their heat. Mouth, the eyes, and a little bit on the inside of the ears. Fur is pretty good at keeping heat in, so the fur doesn't get warm. And there's your temperature scale via color scale. Most of your infrared cameras, you can actually change the color scale to be whatever you want it to be. Whatever floats your boat. Alright, that's infrared for you. The next division that we have is visible light. Really? Do I really need to tell you? Really? See with it. So you have two organs embedded in the front of your skull that can detect electromagnetic waves. But it's only a very narrow range of frequencies. Inside that very narrow range exists all the colors that your brain interprets. And it's all just interpretation. Color is not a thing. It's your interpretation of different frequencies of electromagnetic waves. Color is not a thing. It's an interpretation. Mind blown? No? Okay. Oh, by the way, that's how people can be colorblind, because if the wiring's not quite the same as everybody else's, you don't see the same colors as everybody else. Okay. You do need to remember one thing for visible light, though. Roy G. Biv. The colors of the rainbow from lowest frequency to highest frequency. That's largest wavelength to shortest wavelength. Get it? Low frequency, bigger wavelengths. Higher frequency, smaller wavelengths. There's no indigo, so don't go there. That I just put there to make it sound like a word. There's no color indigo. Alrighty. And ultraviolet waves. This range of frequencies starts to cause damage to living cells. There we go. So this is what causes sunburns, but it's also useful for killing bacteria. UV light in hospitals. Yeah, okay. Yeah, the hospitals use UV light. I got a little toothbrush thing and use UV light to clean the head of my toothbrush. Kill off any germs on it. Alright. Also, there's a thing called fluorescence. So these minerals in regular light, these minerals in UV light. You can't see UV light. Your eyes don't pick it up. There's certain minerals inside these rocks that absorb the UV light. The molecules will do that. And then will not reflect. They absorb the light, it excites the electrons. Electrons go back down to their energy levels, and when they do, they release light you can see. So they absorb UV light and give off visible light in various colors. You got what, purpley blue there, you got pinky red there, you got green. Whereas in normal light, these look, I mean, they're kind of pretty, but they're not all glowy. Here they're glowy. If you ever heard of people that have fluorescent tattoos, the ink used for those tattoos is not visible, but it will absorb UV light and give off visible light. So they only show up at raves, or anytime you put UV light over them. Which, yeah, it's kind of cool, but I mean, when can you enjoy having that tattoo? How many raves are you going to go to? Seriously. At some point, you're too old to go to raves. Trust me, I know. Oh, also, scorpions fluoresce. Should I have warned you that a scorpion was coming up? Yeah, sorry. So that's useful information, maybe? If you hunt scorpions for a living, which, yes, people do. So scorpions are poisonous, you know, little stinger there is poisonous, and some of those poisons can kill people. So where scorpions live, all the medical centers have to have antivenom. Antivenom has a very short shelf life. It goes bad quick. So you have to constantly restock it, either use it or replace it constantly, which means you need a constant supply going out. So the way they make antivenom is by using venom. The process has to start off with actual scorpion venom. Some species of scorpion live very well in captivity, so people will keep them in little terrariums, grow them, milk them for the poison every now and then, and sell it and make the money that way. Some species do not do well in captivity, but they still exist, and they still sting people, and so you still have to get the venom. So people go hunting them. They go out at night with a big old UV light out in the desert, and they just shine it down, and they see something big and green glowing in the dark, so they can find it. Scorpion doesn't know it glows, but we do. They catch it, they milk it, they release it, and they sell the venom that way. Alright, the next type is called the X-rays. Next best division is called the X-rays. I think you know what we use these for, to see hard tissues in the body, which is basically your bone. You can also, there's these people that have to take X-rays of their intestines. It's either cut you open and look at them, or you drink this disgusting barium shake kind of thing, and it goes into your intestines, and the barium will absorb X-rays so they can get pictures of your X-rays of your intestines that way with the X-ray machine, and then it comes out. Enough of that. We also use X-rays to screen luggage at airports. Yay. So the next picture I'm going to show you is the first X-ray that was ever taken to prove the concept. It was the lady who was working on X-rays, so you'll be able to see her wedding band. And I think her engagement ring too. There we go. Alright, so you see the bones of the hand. First little part of your digit right there. Second part. Third part. The knuckle you use to punch people with. This bone here is in your palm. So 1, 2, 3, 4 bones in your palm. 5 bones in your palm right there. Your thumb only has 2 segments to it. See the part that flares out at the end? You can barely see it there, and see right there, it flares out at the end. That's the nail bed. So the nails grow off of that. And there's the ring in the right spot, because that would be right there. Right where my ring is. Haha. Okay. And remember, this is a negative image, so it's reversed. So it looks like a right hand, but it's not. It's a left hand. Okay, the next image is slightly disturbing. It's a 2-headed snake. X-ray of a 2-headed snake. Dang it. There we go. Oop, let me get out of the snake's head. Alrighty. Yay. 2-headed snake. Not very exciting, is it? Not sure why this is so thick right here. It's hard to see the bones here. I'd love to see this area right here where the 2 spines come together, but oh well. Alrighty. That leaves us with one category of electromagnetic waves that we haven't gone over yet, and that's the gamma rays. highest energy, which means they have the smallest wavelength and the greatest frequency of the electromagnetic waves. We do have a use for them. You can kill cancer cells with them. But you got to be careful because that's going to kill the rest of your cells too. So how they use gamma rays to kill cancer cells. This is at least one type of the machine they use for that. They put you on the bed, they slide you in. They have multiple sources of gamma radiation coming out in beams. And y'all remember constructive interference? These are waves. So they aim all those separate beams at your cancer tumor. Right? Wherever it is in your body. And they all converge there. They all meet there, creating a more intense wave right there. The gamma radiation goes through the rest of your body to get there and causes damage on the way, so you will get sick with radiation sickness. Right? There are ways of dealing with radiation sickness. So that's why you can't just do radiation therapy after radiation therapy after radiation day after day after day until you kill it. You need time for the rest of your body to heal up before you take another dose of radiation. And you get sick, and you feel like crap, and you lose your appetite, you lose your hair. It's not pretty. Some of you have relatives that have been through it. You know what I mean. Hopefully it works. But on a lighter note, no matter how much gamma radiation you take, you will never, ever turn into the Hulk. Sorry. That's the 1970s TV version of the Hulk. There. The actor's name is Lou Ferrigno. He's still alive. And he's still just as buff. That man's incredible. Also, stone cold deaf. Couldn't hear a thing. Still can't. Alrighty, that's the end of the PowerPoint. Let me make my face bigger. You have a worksheet to work on, and the answers will be attached to this assignment. And there will be a question to answer when you're done with everything. Then click Submit. Okay?